Here we would like to look at the energy across a hydraulic jump. Basically, what happens to the energy of fluid particles as we go from upstream to the downstream. And let me again start by drawing our famous schematic. So this is the rigid flat surface, and then we have a stream coming, and then complications, right, all sorts of things, and then the downstream side. So the question is, well, what's the relationship between the energy of upstream and downstream? And to answer this, I can consider two different streamlines. One streamline on the surface. So let's calculate the difference between the energy of the streamline, of the same streamline upstream and downstream, and another streamline on the seabed, or on the bottom of the system. So for simplicity, I'm going to pick a coordinate system with x-axis to the right, z-axis positive upward, measured from the surface of the rigid surface that we considered. Now, energy of a stream of fluid at any given location is given by the kinetic energy, 1/2 rho v squared is per unit volume, plus rho gz, which is the potential energy, and then we have a pressure term plus p. So basically what we need to calculate is this quantity in the upstream and downstream. And let's start naming these, like this is 0.1, this is 0.2, this is 0.3, and this is 0.4. So let's write from, let's calculate this quantity at 0.1 and 2. And basically we want to compare and see if the energy has increased or decreased. So all I need to do is to compare this quantity at 0.1 and 2. So I have 1/2 rho v1 to the power 2 plus rho g z1, which is h1 plus p1, right? That is equal to 1/2 rho v2 to the power 2 plus rho g h2 plus p2. But 1 and 2, they are both on the surface. So the pressure is atmospheric pressure, and therefore these can be cancelled. And then I'm going to have 1/2 rho v squared plus rho g h1, 1/2 rho v squared plus rho g h2. Probably I can, before moving forward, I can just do a little rearrangement. So it's going to be v12 minus v22. Now, well, this is not equality. I want to see what is the relationship here. So I want to compare this with rho g h2 minus h1. All right. And then again, I can just cancel the rho. All right. And that's it. Now, moving further forward, I'm going to need the results from momentum equation and the conservation of mass. I'm going to just paste the result here. Okay. So the first equation we derived from the momentum equation. And the second equation is from the conservation of mass. All right, so now using these two equations, life becomes simpler, because now this equation is 1/2 v1 to the power 2, right? And instead of v2, I can simply put so let's just put 1 minus, instead of v2, it's v1 h1 over h2, so h1 over h2 to the power 2. And I'm going to compare this with the other hand, which is g times h2 minus h1. I want to see the relationship. And therefore, this is going to be v12 over 2, h2 to the power 2 minus h1 to the power 2 over h2 to the power 2, comparing with g h2 minus h1. Still comparing. So now I can write this as v1 to the power 2 over 2, h2 minus h1 times h2 plus h1 divided by h2 to the power 2, g h2 minus h1. And this h2 minus h1 can be cancelled. Now, the next, what I'm going to do, I'm going to substitute v1 to the power 2 from this expression. All right, and let's see what we get. So I have g over 2 h2 h1 h1 plus h2. All right, and this is v1 2, and then the rest I'm going to put it with green, so there's going to be another 2 in denominator. There is h2 plus h1, that 1 is missing here. All right, there you go. So there's going to be h1 plus h2 to the power 2 divided by h2 2, and on the other side I have only g. Okay, now one of the powers of h2 that goes away with this h2, and then g goes away, this g with this g. I'm gonna left with h1 plus h2 to the power 2, and then 4 h1 h2, and this is gonna be 1. Again, still there's a question mark that we want to find out the relationship. So that is going to be h1 plus h2 to the power 2, and 4 h1 h2. I can subtract 4 h1 h2 from both sides, and I'm going to get h1 minus h2 to the power 2 and 0. And clearly the quantity on the left hand side is always greater or equal to 0, so this is going to be greater or equal to 0. It's going to be equal to 0 when h1 is equal to h2, i.e. when there's no hydraulic jump. And if h1 and h2 there's any difference, what's going to happen is that the energy on the upstream is going to be higher than the energy on the downstream. So definitely this analysis shows that the energy at point 1, I can just write down here the summary, E at point 1 is higher than energy at point 2. Now we can do something similar between point 3 and 4, and I'll try to squeeze that here. So now what is energy at point 3 compared to energy at point 4? Alternatively, I can calculate the difference between the two, but again, this is another way to do it. Energy at point 3 is 1/2 rho v3 to the power 2, which is the same as v1, because we assume that the velocity is uniform. There is no z, and then the pressure is simply rho gh, and that's it. On the other side, I have 1/2 rho v4 to the power 2, and then rho g z is 0, but p, the pressure term, it's not 0, so it's going to be rho g h2, and this is h1, right? And as you can see, it's basically simply identical to the other thing that we did here. There you go. So I can just write this as 1/2 rho v3 is the same as v1 to the power 2 minus v2 to the power 2, and rho g h2 minus h1, right? So this comparison, if you look, it's identical to this comparison that we have here. So basically the rest is going to be the same, and we're going to get the same result. So basically the conclusion is E3 is greater than E4. And this, through this analysis, we basically showed that we lose energy as we cross a hydraulic jump. And that should be it.